So we'll just kick things off. First and foremost, I am not a data scientist, so please take everything I say with a grain of salt, and feel free to, put me down afterwards. Hopefully not during my talk and tell me how wrong everything was that I talked about, but hopefully it's not that bad. But so yeah, I'm Mark Mager. I do malware research at Endgame. Reverse engineering, software dev a bit. And I've primarily been working on ransomware protection research for the past couple of years. So this kind of dovetails into the research that I did for this project. So just to go over the agenda for today, I'm going to give a very brief overview of ransomware, current ransomware detection methodologies, what ransom notes look like typically. Then I'll delve into talking about exploratory research, then some results that I got from that initial research that I did, and then the development of a point of proof of concept framework, along with the results from that, and wrap things up with a conclusion and hopefully have time for questions at the end. All right, so a very brief overview of ransomware if you're not familiar with it. It's simply just malicious software that's going to encrypt files on your hard drive to deny users access to them. It's going to typically target common file extensions, so PDFs, text files, docs, Excel spreadsheets, things of that nature. Basically, they want to get the most bang for their buck without encrypting every single file on your hard drive and making the system completely useless. There's going to be two types of output that are produced from ransomware. The most obvious is going to be encrypted files. And then typically it's also going to produce ransom notes on disk, and we'll get into the purpose of ransom notes in a bit. So the current state-of-the-art for detection methodologies you can break down pretty neatly into two categories. You have static detections, which are ones that are going to take place without any sort of execution of code of the ransomware. So they're going to be either more AV kind of typically oriented, where it's going to be based off of heuristics or signatures, or something that's a little more next gen that's going to be based off of something, some sort of machine learning model. The benefit to those, obviously, is that all data is going to be preserved and that no code will be executed. But the drawback to that is that if you do miss that detection, then essentially your entire host is open to compromise and all that data is going to be lost in that process. For dynamic detections, there's a few things that can take place. One approach is to plant canary files onto a system, and basically the purpose of these is they're going to be monitored, and if they're modified in any sort of way that a user wouldn't, then that's going to be essentially their trip alert to say, hey, there's anomalous behavior taking place on this host. So that's one approach. Along that same line is just having something an agent run in the background and monitoring processes, searching out anomalous behavior. So the benefit to a dynamic approach is that you essentially have, while the processes are ongoing, you have a chance to detect the ransomware. The drawback to that, though, is that in that process, you might be sacrificing essentially a large amount of the files in hopes of the eventual detection. So how can we improve these two categories of detections? Well, the easiest way to do that is to combine them. So a static and dynamic approach is a layered security approach that leverages the advantages of both is the most ideal scenario that you want. You obviously want to be able to detect something before any sort of code exists. That's the most ideal scenario. But if that doesn't work out, you still want a fallback that you can rely on that may eventually detect the ransomware executing. You can tailor your machine learning model to specifically classify ransomware instead of just generic malware. There's definitely a lot of research that can take place in that. And then trying to improve the dynamic detection methods to pick up on anomalous behavior a little more quickly. And that's the goal of the research that I sought out with this project. So going back to ransom notes, as I discussed earlier. So the basic idea with a ransom note is that it's something that is dropped to disk in order to solicit a ransom payment from the victim of the ransomware. So phrases such as "your files have been encrypted," "Payeson will decrypt your files," things like that, that's what you're going to see in a ransom note. There's multiple file types that ransom notes can take on. The most typical that you'll see is .txt or just plain text file. There's also formatted or rich text formats such as HTML and RTFs. And then there's also images, JPEGs, PNGs, things along those lines. Ransom notes are typically going to be one of the first files that are written to disk. That's not always the case, but it's typically what we see. And in certain ransomware families, ransom notes are going to be written to every single directory on the host. And sometimes, if not every single directory, it's just every directory that is going to that sees a file that's encrypted within it will have a ransom note as well. So essentially, they're trying to be as annoying as possible to try to get their point across that they really want their money. So here's a example of a ransom note. This one's from CryptoLocker. This kind of goes over some of the phrasing that I had previously discussed. The first thing they lead off with is saying your files have been encrypted with CryptoLocker. They tried to describe essentially what encryption is. They want you to contact them. They're giving you a certain expiration date for how long the files are going to last. They're saying antivirus is not going to help you at this point. And then they even get into explaining the AES for you. Here's another example. Now that you saw the first one from CryptoLocker, now you see this. It basically says the same thing. All your files have been encrypted. They talk about specific document types. They talk about decrypting. They want you to send Bitcoin to their address, and they even say thank you at the end, which is very nice. And there's this one, which is actually a image in this case. Their ransom payment is 100 Bitcoin, which currently translates to about $750,000. So not sure exactly who they're targeting with this specific ransomware, but and they're also giving a very specific expiration date. So different approach with that one. So as we've seen, just from looking at 3 ransom notes right in a row, how you can start to come up with a template for how ransom notes look. Your files have been encrypted by insert ransomware name. Sometimes they're going to explain intricate details of the encryption, just to scare you a little bit, say AES-256, RSA-2048, whatever. They're going to explain that your files can't be decrypted on their own. They want you to send a ransom payment to whatever their wallet ID is. You can optionally email them as well, and they're going to give you an expiration date. So knowing all this, my basic idea, and I kind of mix around this in my head for a little bit, is definitely very much a data science novice. So I wanted to figure out a way, hey, can I apply a data science to essentially detect ransom notes as they're being written to disk? And can we differentiate them consistently from normal text files? So with that in mind, first goal was to develop familiarity with the data science concepts and tools that I'd be using. And I'd go out and collect, build up a good collection of ransom notes. And then on the flip side, I'd also need to put together a base benign data set that I can compare the ransom notes to, and then determine how suitable ransom notes are to classification and how solvable this problem really is. So, quick overview of tools I'd be using: Anaconda, Python 3, doing most of my work in Jupyter Notebook, Scikit, and Spacie. Okay, so for data sets, benign data, the easiest thing I found to use was just the 20 news groups data set, and that's around 11,000 samples. That spans 20 news groups that were, I believe that data was collected, like in the 90s or somewhere. So it goes way back. There's the the categories all kind of listed out there. And then the ransom notes. So the way I collected those was from actually manually detonating ransomware samples in virtual environment and collecting artifacts. So that made up a certain portion of the corpus of ransom notes. The rest came from just combing through security research, blog posts, Twitter, downloading actual text notes when they were made available by Pastebin or whatever, or actually downloading screenshots of the ransom notes and then using OCR to extract the text. So to get into the approach that I'm taking for the exploratory research, what we're working with at the moment or for this problem is it'll be unlabeled data. We'll take the ransom notes and we'll take the 20 news groups data and we're going to throw them into one unlabeled data set. And we're going to leverage k-means clustering and set it to sort the data into 21 clusters. And the reasoning behind that is we have the 20 news groups and then we have one set of ransom notes. So ideally what we'll see is the ransom notes all cluster into one tiny cluster, and then the 20 news groups all sort out into their own individual clusters. In order to get a better idea of the data we're working with, we'll also use a bag of words approach with Count Vectorizer, and then also use TF-IDF to also look at the features. So first things first, we need to do a little bit of data preparation. So all we're going to do here is strip out any sort of new line characters. We're going to convert all strings to lowercase. Then we're going to actually do the tokenization. And so we're splitting a large string into just the individual words, and we're going to strip out any sort of stop words like the, a, an. Anything that's going to be within the, I think, Spacey's default stop words list. Then we're going to go from there to only taking into account alphanumeric strings. And then we're going to go ahead and lemmatize the strings and basically convert them to a more generic form of the specific word. So with this very simple sample here, what we're going with is we have essentially a string that we kind of constructed that was describes a very basic ransom note, and then we run it through our cleaning routine in order to clean everything out. And what we end up with is a pretty simple string in the end: file, encrypt, send, Bitcoin, ransom, payment. And you can see how that definitely ties very closely with what you would think a ransom note is going to portray. And when we're taking into account the Count Vectorizer and the TF-IDF Vectorizer, we want to get an idea of what the top words are going to be. What sort of phrases are we going to typically see? And it kind of hits along the same sort of notes that we've been seeing so far. So we're talking about files, Bitcoin, encryption, decryption, sending payments, emails, computers, things along those lines. And then when you break it out to bigrams, it makes a little more sense in terms of phrasing. Files are being encrypted, files are being decrypted. They want you to send in money for a private key, Bitcoin address. Things along those lines. So it gives you an idea that this language is very kind of tightly coupled together. Before that was I was just looking at the bigrams with the Count Vectorizer as well. Now this is the TF-IDF versus the Count Vectorizer, and so with this we're still kind of seeing the same sort of words that are popping up. They're moved up and down in terms of relevance a little bit, but generally it's the same data. And so now going back to the clustering, the way things kind of sorted out is here's a very high overview of the top, I believe, 10 terms the top 10 features for each cluster. And so our ransom notes all ended up very nicely put together in cluster 3. As you can kind of see, they hit the same list of features that we'd previously seen with the top words. And just for reference, the news group 20 categories are listed over there to the right, and you can kind of group together if you start looking at some of the other clusters, which specific news group they might come from. And so, delving into the numbers a little bit, we can see that if we actually calculate the distance from the centroid for each of the clusters for the particular phrase that we're going to feed into our vectorizer here, so we're actually through a legitimate ransom note that we ripped from one of our samples and provided it to the vectorizer, and we wanted to get a idea of which cluster that's going to essentially tend towards, and lo and behold, that was cluster 3, which is the cluster that has our ransom notes in it. And so if we come up with a phrase that's similar to a ransom note, but actually isn't portraying the exact purpose of a ransom note, we'll see it actually doesn't sort it into cluster 3. While it uses some of the same language, it's not using it in the same manner. So it actually ends up in cluster number 4, which is actually a news group for computer graphics. So the results out of the exploratory research. Well, despite a very small set of data, and to go back, we only had 173 ransom notes. The ransom notes clustered together very well, so they use a lot of the same language. And with the second sample example that I showed there, with the subtle different phrasing, there is some nuance in how the data is clustered. It's not just going to throw anything together that says file and encrypt. There's definitely more to it than that. So seeing how the clustering worked out, we're going to say that the data set seems appropriate for classification. And didn't have time for it, but a TSNE visualization would have been very nice for this project, but didn't get around to it. Okay, so building a proof of concept framework. So what do we really need? Well, we need a way to obtain file change events in near real time, and we need a way to pass those file paths into a something that's going to read in the file contents and essentially determine if the text comprises a ransom note. And then if we've determined if it's a ransom note, we need to go ahead and suspend that process and alert the user. So since this is a pretty big problem to kind of take on, I want to put out some restrictions on how this is going to play out. We're only going to work with English notes. We're going to restrict things strictly to text files. The reasoning behind this is any sort of formatted text is going to require additional parsing, and I believe that was kind of outside the scope of the problem that we're working with here. Any sort of images, we're going to have to use OCR for that. Again, that's kind of outside the scope of the goal for the project here. And we're also going to restrict files to file sizes that are smaller than 20 kilobytes. The reasoning behind that is once you start looking at enough ransom notes, you'll notice that a vast majority of them are smaller than 2 kilobytes. And so if you provide a little bit of space there for some of the larger notes that actually provide like a the whole modus operandi behind their ransomware campaign and that sort of thing, then yeah, like some of them bump up a little bit, but generally they're going to be very small notes. They're just trying to get their point across that your files are hosed and you need to send them money. So the way we're going to break things out is into 3 distinct components, but they're going to run within 2 processes. So we'll have a file change event listener, and the goal of that is it's going to take new file events and place them into a queue for the second process, process B. There's going to be a component that will handle the text extraction and also the machine learning classifier that will retrieve the events from the queue that process A is depositing into. And the process mitigation handler will also be in process B, and that's only invoked if the classifier finds a ransom note. So here's kind of a good overview of how a detection scenario would play out. The ransomware is going to execute and drop a ransom note in the root of the C drive. The event listener is going to be pulling for new file change events, and it gets the file path for ransomnote.txt into the root of the C. It passes that file path to the text extractor and classifier. The text extractor will read in the contents of the ransom note, pass it to the model, and then the classifier returns yes back to the event listener, and then the ransomware will be suspended. So for the framework, what we wanted to do is come up with a data set that was going to be a little more reflective of what we might typically find on a Windows host. And so we took a subset of the 20 newsgroups data set. We're going to stick with around 8,000 messages this time. And then also we pulled in a little over 3,000 text files from Windows hosts. And these mostly comprised of log files, readmes, installer files, things of that nature that you might typically find on a Windows host. So we ended up with around 11,000 files or so. And yeah, that's kind of what we build off of. With the ransom notes, we essentially doubled the size of our sample set. I was able to find a few more resources for pulling down ransom notes, so that helped build that up a little bit. And despite doubling the size of the set of ransom notes, that still leaves us very outnumbered quite a bit by the benign data. And so for the POC framework, what we wanted to do was try to address the data set imbalance. And so we're going to use Smote to generate our own synthetic data to try to make up for that. So the approach for the classifier, we're going to use TF-IDF for our feature selection, use a TF-IDF vectorizer. And what we're doing is we're breaking this down into a supervised learning problem. We're using labeled data here. We're distinctly labeling the ransom notes this time, and then we're distinctly labeling the benign data this time. And we have a binary classification problem. If we're provided a block of text, is this going to be a ransom note or is it benign data? That's all we're trying to answer. And the approach that we decided to use is naive Bayes, and more specifically the multinomial NB. So here's what our data processing pipeline essentially looks like. We start with our labeled data set, comprised of ransom notes and benign text. In our pre-tokenization step, we're going to strip out characters, convert all the characters to lowercase. We're going to do the tokenization then with spaCy. And then post-tokenization, we're going to only keep the alphanumeric strings as before, strip out stop words, carry out lemmatization. Then we'll convert that set of data then to vector using the TF-IDF vectorizer. And then we'll address the data set imbalance, as I previously mentioned, using Smote. And then the training will take place with our naive Bayes classifier. So for testing, we're going to split into a 80-20 subsets using train test split. And, just to, it's probably, might be known by most of you guys, but, just going over some terminology here. For accuracy score, that's referring to the accuracy of the actual classification. FN score is a weighted average of the precision and recall. Confusion matrix just provides a overview of false negatives, false positive, true positives, and true negatives. And in terms of the cross validation, what we're going to do is it represents testing the model's ability to predict new data that's not being seen previously. And so the goal with that is that you want to run multiple runs with different training and test data sets. Essentially to test the model in as many ways as you can. And for our purposes, we're just going to use Monte Carlo using a shuffle split. So with one single test, we actually ended up with pretty good results. 99.54% accuracy, 91.86 F1 score if we scale up the value to 100. And with our confusion matrix, results look pretty good as well. We have 0 false negatives, only 14 false positives, and everything else seemed to sort itself out well. But a single test doesn't really show you enough about the model. You might just happen to come upon an outlier, and since we're doing the 80-20 split with randomized data sets, maybe we just happen upon a very lucky set that's going to make our numbers look well. So with the cross-validation, we're going to run it 10 times with randomized sets. And so the cross-validation, as you can see, Steve Ballmer and Bill Gates are still clapping and dancing up there for the Windows 95 launch release, so things are still going well. Average accuracy is about what we saw in our one run. F1 score about the same, and the confusion matrix looks about the same as well. So I think in our specific case, that confirms that the data does classify extremely well. Here's a graphical representation of the scores that I just kind of showed. Some fluctuation in the F1 score, but they generally at least stay above 85 or so. Accuracy stays extremely high, above like 99.3% on average. As again I said, I'm not a data scientist, but I believe these are good results. Okay, so now going back to our event listener. So essentially what we need is something that's going to monitor file change events for us. We need to monitor all processes on the host, and what we need is a mapping of each specific event to a specific source process. And in particular, for our case, we want to monitor file creation events. And so there's a few ways that we could go about this, but some of them aren't going to hit every single of those three objectives, or they're going to hit them, but it's going to be a little more difficult, right? So since our code base that we're typically using is Python, first thing that comes to mind is you might want to use Python Watcher. The problem with that is it relies on the read directory changes API, which I believe only operates on a specific directory, is a little noisy, actually is a pretty big drag on performance, and to top it all off, does not provide a mapping of a specific change event to a specific source process. And the reason why that isn't suitable for us is that we would have no idea what process that specific event comes from, and we don't know what process to suspend or terminate in that instance. So essentially, if we're using this as a detection framework, the output of that's going to be pointless for us. We would just know that there's a ransom node on the disk. We have no idea what stopped it. So what are we going to do? Event logs, that'd be one way of obtaining events for our purposes. Or you could also write up a file mini filter driver. File mini filter driver in the long run is definitely the best approach to take, but it's also the most time consuming. And if you're writing code for the kernel, you're definitely prone to make mistakes and crash your box. So what do we do in this case? Well, luckily for us, there's Sysmon. And within the last year or so, Sysmon, they opened up their framework for exposing file creation events that they're going to write to their own event log. And so with event ID 11, all we need to do essentially is query the event log for file creation events, and we're going to get all the data that we need. So in order to reduce the noise that Sysmon creates, because if you ever installed Sysmon and query the logs occasionally with just default settings, there's going to be a lot of noise in there. So essentially, I just created a very simple stripped down config file to just eliminate any sort of process creation and termination events, and limit it only the file creation events only to .txt files, and that's right there, the simple command that you need to run in order to get Sysmon configured to work with this framework. And then also to query the logs via WMI, you need to specifically add a event key or registry key to allow event log querying. So as I mentioned before, what we're trying to do is pull the event log for new file paths, and we're going to be using the WMI query language. We need to limit the size of the result set in order to reduce overhead because the event logs can build up over time. And we need to parse that data from the results and then pass that to our classifier work queue. So in terms of the process mitigation, all we need to do is, like at this point, we know that there is a ransom node on disk. We know the source process, and we also know the source process name. So now we need to determine if that information is still accurate, if their process still exists. So we're going to grab currently active processes to try to determine if that process still exists. If it does and it's still active, we're going to suspend it. We're going to provide a pop-up to the user to tell them that a ransom node was detected, allow them to terminate or resume the process. And also, if they do resume the process, we need to maintain a whitelist of process IDs and process names so we don't just keep alerting over and over on the same process. And so at this point, I'm going to do a live demo. Let's see how this works. A lot of confidence behind this. Okay, so what we're working with here is a sample of the Volcano ransomware. And so right here I have Process Monitor running in the background. I already have a filter specifically for write file operations that are going to be written out by the volcano.exe process. And so I'll execute this. And that was pretty quick, wasn't it? So what we have here is it lists out the file path of the ransom note. It tells us the specific process, the source process path, along with the specific PID, and then it's giving us an option. Click OK to terminate, or cancel to resume and whitelist the process. For further confirmation that this worked, 24292 volcano.exe process explorer is telling us that's suspended. And if we go to the process monitor output, we can see how fast that actually took place. If the first file write was at 536.55 here, we're going to scroll down here. If I can get this. 536.56. So essentially 1 second after the file writes begin is when our detection kicks off and we suspend the process. And we can even drill down even further into this to see just how long it took for us to detect as soon as we saw a text file. So as we can see, the first ransom note was written out to the install4j user, well, actually just the install4j directory, or actually that's the one that we detected on, but the file writes took place within milliseconds of each other. So depending on how they're pulled from the log, one might be seen before the other. But essentially, as soon as the ransom note first hits the disk, we're going to obtain the file paths by querying that event log, and we can see things. And so if we go ahead and click OK, terminate the process, voila, volcano.exe is no more. And I'll tempt the demo gods one more time here and actually do one more demo here for you. I'm going to run a sample of BTCware. I believe I have the filters all set up. Oh, actually I didn't. That would have been bad. So yeah, just going to set up my procmon log here just to give us some more of the output. Okay, so if we run BTCware, and we caught that one as well. So you can see that in this case there were a few more file events that took place before we actually came up with our detection. I mean, it's definitely going to vary from case to case depending on how performant the querying of the event logs is going to take place. You know, as I kind of alluded to before, all of our codes running in Python. We're not running our own mini filter driver. We're simply just querying an event log repeatedly every 10 milliseconds. So it's going to be a drag on resources, and you know, even doing some like sort of timing analysis, I noticed a lot of different you know, results in terms of how long the queries were taking place. So not ideal for some sort of production ready environment. Like, please don't deploy this to your 10,000 endpoint network. I take absolutely no responsibility for what happens. But you know, for a limited proof of concept, this definitely gets the point across, and you can see that process is also gone. Okay, so getting into a few more results, I had time to test this out on a few other newer samples. So 9 samples, 2 of which that I showed you tests for, BTCware and Volcano, were able to test and detect those ransomware samples. So for those specific samples, what makes those a little more unique is that those ransom notes weren't previously seen. They weren't included in our training set at all. You know, that's essentially new data that comprises a little bit of a holdout set, you know, for us in this case. There's also 3 samples that I specifically tested that have ransom notes that are in our training set that we're able to, you know, test and detect as well. So in order to get a better idea of what this really, you know, kind of brings to the table, I wanted to produce some comparative results. I wanted to compare what the capabilities of this framework are versus you know, what else is out there in terms of free ransomware detection capabilities. So we're going to be doing 2 very well, unscientific tests here. Test 1, does the product detect the sample? I mean, that's extremely straightforward, so not pulling any punches there. Test 2, we're trying to detect which is faster, the classifier framework or rival product A or B or C. The reason with this, you know, that it's, you know, maybe not the best way to measure it is that there's definitely potentially a lot of different complicating factors, one of which could be driver altitude. And assuming that most of these products are going to be based off of file mini filter drivers, the altitude in which the driver is installed could determine, you know, which driver gets to see the particular file path first and do its analysis before it releases its access to the file path, you know, for the next driver on the stack. You know, don't exactly know how that factors into things, and you know, wasn't particularly interested in reverse engineering all these products. Yeah, but you know, definitely take these results with a grain of salt. So without naming names, I was told to avoid that. I don't want to cause anybody any problems here. But product B, in our case, performed the best and also was typically faster than our framework. There was only one instance, I believe, where our framework detected something before it, but most of the other results were either ties or the product B was faster in its detection by a second or 2. But as for product A and C, product C in particular, you know, had pretty spotty coverage in terms of detecting ransomware, and even well, when it did, it at least outperformed the framework. But product A in particular, yes, it at least seemed to cover all the cases, or you know, 11 out of 12 samples. But in every instance but one, you know, our humble little Python-based framework that's querying event logs every 10 milliseconds was able to outperform it. So with that being said, to bring us back down to earth, there are definitely several limitations involved here. Despite the very promising results that I just showed you, it's definitely a little bit of a loaded sort of test there. It's a loaded scenario because we're already working with samples that we specifically know drop text file ransom notes, and so at the moment, that's all that it's tuned to use or detect is text ransom notes. So that's one huge limitation, but that's one that we knew at least going in. There are some samples. I don't know any specific families at the moment because I've tested so many samples over the past few years. All the family names run together. But there's some samples that don't drop ransom notes until nearly the end. So when they've essentially encrypted everything on the file system, then they go back and write out the ransom notes, which kind of would defeat the purpose of our framework in that instance. There's some samples that are actually extremely annoying and will install some sort of persistence ahead of time and actually keep respawning the same process over and over, attempting to encrypt more and more files. So in that case, yeah, we might catch the ransomware process over and over, but you're still going to be infected, and there's definitely a lot more work that needs to be done in that case. And then to get into a more wider problem, there's definitely samples that take a different approach to ransomware. There are ones that attack the system in different ways besides encrypting individual files. Some will corrupt the MBR, overwrite the bootloader. They'll do a more full disk encryption, raw disk based approach, or some are just simply very annoying screen lockers, which will make it impossible to just log into Windows on its own without actually corrupting the files in any way. And then last but not least, we're only working with English right now. There's definitely ransomware that targets Spanish-speaking countries, Russian countries. There's Russian-speaking countries. There's a lot of other sort of variants out there, but outside the scope of this talk and this feature for this presentation. So future work. The first thing that comes to mind is we could definitely improve the data sets. We could introduce much more ransom notes, which would mean that we would rely less on our synthetic data. So we need to keep pulling in ransom notes as new variants are discovered. And we could also do a much better job of bringing in a representative benign text data set from different installers, README files, things like that. So you could use Ninite, Chocolatey, some sort of other mass installer to build up a large corpus of text files that are going to be written to disk and kind of pull from there. Alluded to this a few times, but definitely porting to a much lower level language, C, C++, something like that, that would yield significant performance improvements. I mean, and if we also tie into working with a file mini filter driver, then you'd have incredible performance, and we could easily, at least for those cases that I was mentioning, outperform products from very large companies. And parsers for other file types. I alluded to before that the image-based ransom notes that use formatted text, it'd be great to support those. Putting the work in to do those probably shouldn't be too much work. Expanding language support, that'd be great. And actually, finally, to go back to data science, experimenting with different classification approaches would be great. Naive Bayes is just what worked for this particular problem. It's just kind of low-hanging fruit because I kind of pulled a couple of data scientists that I work with, and they told me to go in the direction of using Naive Bayes, and that's the way I went. The results were good enough, so that's what I stuck with. And so, as of now, the source code for all this is available on the Endgame GitHub. It is AGPL v3, and it went live this morning. So, to wrap things up.
Can you go back, please?
Oh, sorry.
Thank you.
Yep. I think I got it at the end too, but. All right, everybody good? Okay, so to wrap things up. with our exploratory research, we used clustering to prove that the data was suitable for classification. We were able to determine that the ransom notes do share enough features across the board that would make this a viable solution product, for this particular problem. And we very much realize this isn't going to catch all of ransomware. But going back to talking about our layered security approach, this can be an integral piece of layered detection and improve the time to detect for dynamic detection when we do happen to miss something statically. As we see, the POC does work, but there are many improvements to be made. And if I can do this, I'm sure you guys can do much better because you guys actually know data science and I don't. Quick little plug here for something from Endgame. Maddie right here will stamp your passports if you guys picked up the passport cards from the Endgame booth earlier. If not, you can talk to us and we'll point you in the right direction. So yeah, thanks for coming out, guys. Yeah, if you don't have questions, you can find me later. Oh. Yes.
In doing this, I realize you're using high-level and sort of low-level language and that kind of thing. Did you do any performance tests to see like how this would work on a file server, so that you could see the difference between that using Python or even assembly, and doing these, because that's really what this comes down to, is you're looking for specific keywords. Mm-hmm. File servers are what you're going to be worst hit by ransomware. So. Oh
yeah, I hadn't got around to like kind of doing any testing with any sort of lower level languages. I think at least for carrying out the POC, it was just easiest to use Python and the performance. Yeah, I mean like you would definitely I could easily see how that would be extremely performant for carrying things out in that way. But yeah, I think that would be kind of the next step is to go down that path and write our own driver, and do all the other data science stuff, at a much lower level language in Python 3. Yep.
Do you know of any vendors that are working on? Do you know of any vendors that are working on solutions for NASs like NetApp and integrating directly into their native functionality?
Not that I've heard of. Most of the applications that I was kind of able to discover are just ones by some more of the main vendors, and they just were kind of tailoring them just to kind of give people a rough sense of how their detection works. And I don't know if that's necessarily their full enterprise support. What they would roll out if you got a big contract for 10,000 endpoints or something like that. Cisco? All right.
I hate Cisco, but...
All right. Down with Cisco. At least, yeah. Yeah, that's the first I've heard of it, though. But yeah, I think as ransomware continues to pick up in prominence, I think that you'll see more specific tailored solutions for different products.
Have you seen any other OSs besides Windows that get targeted for ransomware?
Yeah, so there's definitely a few different like Mac OS ransomware families, but as we've been tracking them, they haven't really evolved significantly within the past couple of years or so. I don't know of any that are particularly successful compared to like the actors behind SamSam or some of the other more prominent ransomware families that you hear about. But yeah, so there are some Mac OS ransomware. There's some Linux ransomware, but I feel like that's few and far between. And actually, the most besides Windows that I've heard about is ransomware that targets Android systems. And yeah, I'm not sure exactly what sort of detection capabilities there are for Android right now.
And in-game ink.
Yep.
Too many dots.
Oh, it's just in-game ink with no dot? Ah, okay. I blame the proofreaders for not catching that. All right. Thanks, guys.